Okay, the video is starting, so I'm actually capturing the audio now. There's a bit of loud time at the beginning because waiting for y'all to take out the worksheet. So we will be starting with the organic chem drill practice that was given last lesson. The eraser thing was not done by me. Okay, so while waiting for y'all to take out your drill practice, I think it's from SAJC. I'm not sure if it's written on the paper. Okay, so just take it out and get ready for to check the answers. Okay. Okay, so just searching for the file where these answers are kept. Obviously, I'm not looking at the right places, so just wait for a while. Okay, it's in my tuition folder, my H2 chemistry, under notes, organic chem. Yes, please inspect my crazy folder of files. Yeah. Under organic chem memory sheet, it should be in, maybe it's not here. Okay, maybe it's not here. Probably organic chem practice could be in this folder here. Yes, over here. Okay, SAJC organic chem drill answers. Okay, let's go. Okay, so this is the first question. Just need to put this screen on TV. Okay, so gonna cast this onto the TV. Okay, if anyone comment on anything, I probably have no idea or cannot recall anymore. So I will not be replying. I will not regurgitate whoever made a comment. Yeah. Okay, so let's look at this. Okay, we will have to draw the structural formula. So for the first three, there are three options. Okay, so just check that there's three options for C5H10. Sorry, some technical loud time. Yes. Okay, to my C5H12. Okay, there are three possible answers, and for C4H10, there are only two answers. Okay, this is just looking at structural formulas alone without looking at the optical isomers. Okay, then after this, we will move on to look at the C4H9Br. So just take some time to check your structures for these two questions. Okay, next one will be C4H9Br. Okay, you can see the first answer is for is a 2-bromoethane. Okay, then just keep on moving on. Just check your answers for C4H9Br. There are a total of 4 options. Okay, try to draw the skeletal. It's a good time to actually practice getting used to the skeletal diagrams. Okay, now if you're done with your C4H9Br, check for C4H10O. Okay, do take note that your answers are not limited to alcohol. There's also ether. Okay, so if you count, there's actually 1, 2, 3, 4, 5, 6, 7. Okay, there are only 7. Okay, one of them is actually the same repeated one, so they are not isomers. Okay, so there are 3 possible answers for ether and 3 possible answers for alcohol. Sorry, 1, 2, 3, 4, 4 possible answers for alcohol. Okay, so just check that you have a total of 7 structures. Okay, then they ask you to draw the structural isomers including stereoisomerism. You don't need to repeat the whole thing. Okay, just practice drawing your optical isomers. Okay, it's the one with is actually what is this, butane 2-ol. Okay, the optical isomer is on butane 2-ol. Okay, so make sure that the OH and the CH3 is not aligned in a vertical line. Okay, they are kind of angled. OH and H are solid lines and they lie on the paper. Okay, the one with the radial wedge is going into the paper and the one with the solid wedge is coming out of the paper. Okay, so try to maybe have a 3D visualization of how this butane 2-ol will look like in 3 dimensions. Okay, now next one, check your geometric isomers present in these few compounds. Okay, there's a cis and a trans. Okay, I don't think the cis is wrong. I think also maybe because it's in black and white, so the student might have done the corrections on the thing itself, so it looks wrong. Okay, but this answer is correct. Okay, both the cis and the trans options are correct. All right. Okay, moving on. More cis trans. Okay, so remember for cis, right, the heavy MR groups appear on the same side of the double bond, and the smaller MR group will be on the other side of the same side but on the other side of the double bond. Okay, whereas trans, they are on opposite side of the double bond. Okay, then also do take note that this can be applied to lone pair also. Okay, so take note that it can be applied to lone pairs. So okay, if you look at the one with two nitrogens connected to each other, we consider their lone pair as the similar group that should be considered as the cis or the trans. Okay. So yeah, these two big squares here actually is to highlight to you which are the heavy MR groups. Okay, so you can see the two heavy MR groups are as per seen. Okay, so you can have the two squares on opposite side giving you the trans isomer and on the same side giving you the cis isomer. All right. Okay, now again here we have another bunch of optical isomers. Okay. Okay, the carbon with an asterisk is an indication of the optical isomer. All right. Then again we can reflect them on both sides. Okay. Okay, just making use of that square to highlight the necessary part again. Okay, now again, optical isomers. Okay, just check your answer. Now let's look at the chiral center. Okay, this one wasn't attempted, so I'm gonna do it for this student. Okay, so there's one over here. Okay, where there is the Mercedes 120-degree angle pattern. Okay, so these two are the chiral centers. Okay, the previous one don't count. Okay, the previous one don't count because two of the carbons actually can have a viewpoint of having the same pattern, or rather the same groups. Okay. And then for this one, the chiral, there's one missing. She's not this one. This one doesn't count. Again, there are carbons that have that view to have the same R group. Okay, so this one is not a chiral. Okay, the other three are. Okay, now if you move on, so take note, okay, because the carbon on the hexagon, okay, can you see this side and this side, right? Okay, you view from the other carbon, viewing from the other side, okay, this carbon, if you look at it clockwise, you look at it anti-clockwise, these two carbons actually are the same group. So this is not a chiral, okay? You can kind of like view it as a meso compound, but it's not exactly the meso compound, but since it's a symmetrical, sometimes you will have like symmetrical, then like you see the R group different, right? But then it's a meso compound. Okay, like in this case, okay, there's one carbon here that actually has a chiral, but student didn't circle it. Okay, I guess the teacher has circled it as a missing answer already. Okay. Whereas some structural easy memory answers or definition answer. Okay, so what is the term geometric isomerism? Okay, this is off my the answer off my head. I'll update with the exact answer a bit later. Okay, but main thing is they have same molecular formula. They do not have different structural formula. They have a same structural formula. Okay, the more important thing is they have different spatial arrangement. Okay, but molecular and structurally they are same. Okay. Different spatial arrangement, like your cis trans and your uh optical isomerism. In the definition for optical isomerism, they have chiral, atom, and then four different groups. Okay, standard answer. Okay, now let's draw the type of stereoisomerism by the following compounds. Okay, this one didn't draw because there's no optical isomer, no cis trans isomerism. And there is no optical isomerism either because the left group and the right group are the same. Okay. Okay, so if you look at this carbon over here, okay, the group, yeah, I'm gonna box it up. Okay, there's this group on the right side and there's this group on the left side. Okay, they are essentially the same group, hence they will not have any optical activity because you need four different groups to uh, have an optical activity. All right. Okay, now this one over here, there's a chiral carbon over here, hence it gives rise to optical isomerism. Okay, so look at this carbon with the asterisk, that's where the chiral carbon is that will give rise to optical isomerism. Okay, and then there are these two carbons over here. This one will have a cis trans, okay, because of the yeah, I just went back to I was supposed to edit. Looks like it's not correct yet. Okay, I'm doing it. Oh my god, my spelling is wrong. It's not molecular, it's molecular. Okay, let's see if I actually edit with the correct spelling. Okay, so this is me being a bit retarded at the computer again. Okay, stereoisomers. Okay, stereoisomers is the same as geometric isomers, okay, remove that thing. Okay, good. Okay, this is my stereoisomers answer. So compound with same molecule, come on, I can type this with a, oh my god, so many typo, with a double bond. Okay, so compounds with a double bond that have restricted rotation. Okay, so doesn't always have to be a carbon, it can be a double bond. So remember the previous example with the nitrogen. Next one example of another with a double bond. All right. Okay, now next question. Okay, state and draw different types of isomerism present in 2-bromo, 1-chloro, They wrote 2 propanol, but actually should be propan 2 all. Okay, I don't know why they name it this way, but it should be 2 bromo, 1 chloro, propan 2 all. Okay, but the compound drawn is correct lah. Okay, and then this carbon right in the middle here is a chiral carbon. Okay, so we can draw the optical isomers for this. I think this is me trying to type the correct name of this compound. Okay, but again, check your chiral, your optical isomers have been correctly drawn. Make sure that your radial and your solid wedges are pointing in the right direction, alright? Okay, oh yeah, there's a bit of a mistake here. It's not a CH3Cl, should be a CH2Cl. Okay, uh, I don't think you will make this mistake. It's quite a glaring one. Okay, so it should be CH2Cl. Okay, don't need to draw any other compound. Okay, as in like you don't have to draw the structural isomers of this because the structure has already been given to you. So you just have to use what is given. Alright. Okay, now so I need to switch back to okay here. I think somebody had a question, so let's look at it. This is me probably trying to figure out where that spot is. Okay, yeah, okay. This is me correcting. Okay, so you see how when the H is pointing upwards like this, is wrong. Okay, the H should be kind of like a 100. Remember 109.5 degree, right? It should be like a 109.5 degree angle from the OH. Okay, as in the hydrogen. Okay, so back to the answer key. Okay, so just make sure that your radial wedge is 109.5 degree or at least looks like it from the OH. Okay, you don't need to bring your projector and measure lah, of course. Okay, just use just eyeball. Okay, more than 90 degree can already. Okay, I guess somebody asked something here that I have to demonstrate. Okay, I guess not. Yeah, multiple screens going on so that you can see everything. Okay, I don't know what I'm trying to do here, but let's see. I think I want to probably go on the TV, I suppose. Okay, next question. Okay, this one also the name, instead of 2-hydroxy 3-pentene, right, it should be 2-hydroxy pen 3-ene. Okay, so the student actually drew this correctly. Okay, just take note of the optical isomer. I know what's wrong with this one. CH. Okay, I see the chiral CH3. Oh, okay, the way the reflection was done. Okay, so I think actually the left hand side is correct. It's the left hand side of the mirror line is correct, the one where it's circled. But the right hand side actually is not very well mirrored. Okay, so it should have been mirrored such that it is an actual mirror. So it should have been CH3CH instead of CH3. Okay, not sure if you can catch any of that. Okay, but okay, I think let's look at the cis trans first. I think I was talking about the cis trans first. Okay, so optical isomer and geometric isomer. Okay, looking at geometric isomer, just make sure that your cis trans, okay, the cis being on the same side, trans being on opposite side. Okay, so this one is the correct one. Okay, where actually it's a better representation in a way lah of both the cis trans and the iso and the optical. Okay, first you draw the cis, then you draw the mirror for it. Then after that you draw the trans, then you draw the mirror for the trans. Okay. Only thing is that this student, the drawing, right, not very representative of the tetrahedral and optical isomer. So try to angle it such that, you know, again, your solid line are 109.5 apart. Then the solid and either the solid line and either the wedget or the radial wedge is also 109.5. Okay, they shouldn't be 90 degrees to each other. Okay. I think I might do a demonstration of the drawing. I remember doing a demonstration of this during the lesson. So let's see if that happens. Okay, let me just move forward a bit. Not sure if I suppose there's somebody asking a question at this point. So let me just move forward so you don't have to wait too long before some action takes place. Okay, I really have no idea what. Let's just wait. This having to do a it feels I'm doing a commentary for a silent movie. That's how it goes, I guess. Double bond that is restricted rotation with similar groups and different carbons. Okay, I'm not sure who asked me a question on during this point, so I have no idea why I'm highlighting this. So let's just wait it out a bit. Oh, oops, I'm retyping this. Cis trans isomerism arises when rotation about double bond is restricted, because that's probably what it's going to be. Actually, yeah, it doesn't have to be a double bond. Sometimes you have compound that have like triple bonds, but they also have restricted rotation. Then they might also have cis trans. All right. Okay, next one. Okay, another naming issue should be 4-bromo 2-methyl pen 2-ene. Okay, this is me finally making an effort to correct the name of the compound. Okay, should be pen 2-ene. Not sure why I keep transiting between the two screens. It's kind of odd. Okay, but anyway, we have different types of isomerism for this. Okay, so if you look at this compound, you should be able to identify an optical isomer. They should not have cis trans because there are two CH3 groups on the same carbon. So no cis trans isomerism or stereoisomerism. But there, wait, sorry, scrap the stereoisomerism. Okay, no cis trans isomerism, but there is optical isomerism. Okay, due to the carbon, the chiral carbon being present. Okay, so again, note the way you draw 109.5 degrees. Okay, and then this yeah, I guess I'm gonna demonstrate or mark somebody's work at this point. Okay, fantastic. I didn't take a look at what's going on here. Can I please shift the paper up? I hope I shift the paper up at some point. Come on, push up a little. There you go. Oh, okay, see the reflection of these two groups, right, is not very well done. Okay, so I'm actually making corrections to this script. I don't know, is it Shu or Uvias? Okay, so the BR should be like reversed, alright? Let's go back there a bit so that I can pause and talk about it. Capture the right place. Pause. Okay, can you see? Okay, it's a bit blurry, but this BR should be by reflection, right? The order should be BR. Then this, since this is CH over here, right? Then this should be HC, right? Then if this is CH2, then this will be H2C. Or if you write C, you can write H2 on the other side. Basically, you have to imagine the way you write it out in a structural formula, right? It has to look reflected. All right. So I guess I'm explaining how to you know what, let me forward a bit before I explain what I'm trying to do. I have no idea what I did at this moment. Uh, 3-chloro-4 hexene 3 all. Then I'm told to do the different isomers, and I drew. Okay, not sure what was going on. I wish I could. Maybe I should have commentary this at a 2 times speed. Let me know if it's better to do a commentary on this two at a 2 times speed. So this compound, 3-chloro, 4-hexene, 3-ol. Okay, so let's draw 6 carbons, okay, for the hexene 3-ol, right? And then there's a double bond at the 4th carbon and alcohol at the 3rd carbon, right? So I drew the double bond in the wrong spot, should have been there, okay. And this is the OH at the 3rd carbon, okay? And then double bond is at the 4th carbon. Okay, then we draw a Cl on the 3rd carbon, okay, shifting it to make it right. Yeah, I think someone else probably asked me how to decipher the shape, so probably that's why I'm showing you how to draw the structural formula. Okay, so we already draw the 4-hexene 3-ol, then we just need to fill in 3-chloro and then just draw the rest. Alright? Okay, so let's look at the isomers, okay, present. So this one has an optical isomer and it also has cis trans. So same story, you can draw the cis and draw the reflection, and then draw the trans isomer and then draw the reflection. Right, then that will give you a total of 4 isomers. Excuse me for the lull period. I think because it's muted during the recording, so somebody might have asked a question I was probably answering, but I cannot remember them anymore. So this is me probably trying to show you how to draw like a cis trans. If cis trans with optical isomer, okay? So you start with drawing okay, you draw like this one is the cis isomer. And then you draw the optical isomer for the cis, okay? So again the two solid line, okay, then the wedge, solid wedge, and then the radial wedge. Okay, then you draw your mirror after this. Okay, so draw the dotted line. Okay. Excuse my fat hand. Okay, so since this is CH2, CH3, right? Then the reflection will be a CH3, CH2. Or you can look at it as a CH3, yeah, CH3, CH2. So this is me cancelling to make it a bit more correct. Okay, so the connection from I think I gave up and drew it in my direction. Excuse that for a while. But anyway, the carbon should be connected to the carbon that it is connecting. So like for example, if you write CH3, right, your carbon should be connected to the C, not the H. Alright. So after I correct it, just give me a moment. I guess I'm figuring out something. Okay, there you go. And so you can see, right, the C, I wrote it as H3C, H2C. Okay, so you read the connection as it should be. The C is connected to a C, then the H2 is connected to the carbon, then you have a CH3 attached to this carbon. Okay, then the rest you just complete accordingly in mirror image. Okay, then you do the same for the trans isomer. Okay, now next one, the next exercise is much easier. Okay, it's all about reagent and conditions. So the first one is free radical substitution. So you should be using limited Br2 UV light to ensure that there is no multi-sub. Okay. Now the second one is wrong. It should be excess since you can see that there's a dibromo present in the product, right? That means there's multiple free radical substitution occurring. So this should have been excess Br2 instead of limited. Okay, with UV light. Okay, then the next one, all right, is also FRS. Okay, so we also use limited Cl2 with UV light. Okay, at this point, I think I remember Shrutika actually asked me, like, can she just write heat? Because in your lecture notes, they write heat or UV light. Technically, it's not wrong, but I think the most accurate or the most common accepted answer is UV light. So just to play it safe and ensure that nothing goes wrong, just always use the UV light. Okay. Next one, okay, you have to draw 5 possible products that can be formed and write the display formula. All right. So this one you can use skeletal formula. It's fine also. Okay, so don't worry, you can use skeletal formula. But you should have 5 possible products. Okay. I don't think they are all structural. So no optical isomers included in these 5. Okay, there are 5 structural formulas that look different. All right. Okay, so what's the ratio of the products formed? Okay, this answer is not very clear cut which ratio they're referring to. So just give me a moment while I will type it out in a bit. The ratio they will form. Okay, basically the number of hydrogen positions that will give rise to the same product would be the ratio of the products formed. But this is not the exact expected answer, or rather the exact ratio that you will get when you carry it out. Okay, because the stability of the radical actually plays a part also. Okay, so don't forget tertiary radical is the most stable. Hence, you will have that in highest proportion, followed by a secondary radical, followed by a primary radical. All right. Yeah, I think there's a bit of a pause here because I'm asking everybody to think about what is the ratio of the products formed based on the number of hydrogen positions that could give rise to a substitution. So if you look at the first one on the left, right, for that particular chlorine position, there's only one possible hydrogen location that can give you this product. All right. So that ratio would be 1. Okay. Then if you look at the second one, okay, where that particular Cl is, there is 3 positions that will give rise to this product. Hence, the ratio for that would be 3. All right. Then I guess I could like move over. Okay, so if you look at this one over here, okay, this 1, 2, and 3 hydrogen positions will give you 3. Then this one over here where this Cl is, okay, there's only 1 position that can give you this product. Okay, so this is 1. Okay. Now the next one is also 3, okay, because this Cl again 1, 2, 3, these 3 are the same. Okay, then this Cl here, there's two positions here, 1 and 2. There, sorry, excuse me. There's a bit of a mistake. Let me go back a bit in this video. Okay, this one, right, should have been a 6 because 1, 2, 3, 4, 5, 6. Okay, this 1, 2, 3, 4, 5, 6 positions will give you the same possible product. So this should have been a 6, not a 3. Okay, I think I took the answer given by OVR. I think it was right, but now I look back, it's actually wrong. Okay, this one should have been a 6. Okay, this one 2 is correct. Okay, so it should be 1, 3, 1, 6, 2. Okay, so let's move on. Maybe like pause for it. Oh, I paused the video, so I was like, what am I stuck for so long? Okay, let's move on. Then move on. No, I did not. Okay, move on. Okay, again, 13162. Okay, am I moving on? Yes, I am. Looks like time is on a standstill. Okay, here. Okay, so just a recap on free radical substitution. Don't forget to write the name of the mechanism. Okay, so and also write the condition UV light for initiation. All right. Then make sure you indicate your homolytic fission arrows. Okay, then take note that the chlorine radical will always attack an alkane to give you a alkyl radical and HCl. And then the alkyl radical will attack a chlorine to give you, well, regenerate the chlorine radical and then give you a chloroalkane. Okay, so this propagating process will continue. And then don't forget to write your 3 termination steps. Okay, so 2 chlorine radicals will meet to give you Cl2. Then, yeah, the other 3 products as shown. Okay, now we draw the structural formula. I think I went pretty fast here because there wasn't much problem. Okay, you all just had to add the products across the double bond. Alright. So just check your answer at this point. Okay, then the next one, again, check your answers. Addition of HCl, adding the Cl2. Okay, I think electrophilic addition shouldn't be something difficult. Okay, at worst is the more difficult thing is probably Markovnikov rule, where you have to decide where to put the hydrogen on the carbon that already has more hydrogen. Alright. Okay, so just take some time, check your answers before I scroll down to the next answer. Yeah, after this checking of answer, this one is take note, is addition of water. Okay, not remove. Yeah, no corn sulfuric acid always sounds like for removing water, but in this case it's addition. Okay, now electrophilic addition. Okay, the second mechanism you learn. Okay, so just do your correct do your heterolytic fission on HBr. Okay, ensure your curly arrow again is from the double bond to the hydrogen. Okay, I think I'm just saving my notes since I wrote so many notes. Yes, replace. Okay, so that's the mechanism. Okay, now oxidative cleavage. Okay, just break the double bond. Any site that has two hydrogen and on the carbon will give you CO2 and H2O. And anything that has only one hydrogen will give you carboxylic acid. And any group that has two R groups will give you a ketone. All right. And this one over here, I think the group had a bit of issues figuring out how to do the oxidative cleavage. So all you need to do is draw a line at each of the double bond. All right, then imagine that whichever was cut off, okay, will give you the relevant product. So this part here with the C terminal CH or terminal double bond C, okay, will be cut off. So that part will give you a CO2 and H2O. This part pointing here, since it has two R groups, it will give you a ketone. This carbon over here has a hydrogen, so it will give you a carboxylic acid. Okay. Then this carbon over here also has a hydrogen, so it will also give you a carboxylic acid. Okay. Then this carbon over here has hydrogen, so you also get a carboxylic acid. And then this carbon over here does not have any hydrogen, so this will give you a ketone. Okay. So that's how you get the products on the right side. Okay. I think after this point, everybody was still lost, so there will be more diagram coming after this, I think. See, there's a scroll back because somebody is asking something. Okay, I think I'm trying to listen to somebody's question. Okay, probably they don't know how to see this is being broken up into separate compounds. Okay, so let's move on. Did I already? Let's see. Okay, we'll come later. Okay, now take note that if you use alkaline KMnO4 and you heat, okay, then the OH is a carboxylic acid and it will react with the alkali. Okay, so on reacting with this alkali, then we have to remove one hydrogen, okay, because this hydrogen acts as this carboxylic acid acts as an acid and it donates a proton. Okay, remember your Brownstedt-Lowry acid-base definition. Okay, so this acts as an acid and then it will gain a Na plus as a cation. So it's kind of like a sodium metanoate salt. Not kind of, it is. Okay. So not sure what am I pausing for. Okay, but just remember if you use hot alkaline KMnO4, very important, hot alkaline KMnO4, any carboxylic acid in your product will react with the alkaline to give you a salt. Okay, basically it loses its proton. Okay, so similarly here, there's OH, and since that part's a ketone, as a ketone, nothing happens, but here is a carboxylic acid. Okay, so see where this portion here is being cut off. Okay, you get a carboxylate on this side, and that will now give you, okay, and then there's another one being cut off. So I think some of the students in the class actually had a confusion on how it looks like after this has been cleaved. Okay, so we'll go to that in a moment. Okay, but again, this side being a carboxylic acid, okay, it will give you a salt, okay, by losing its proton. So you'll lose this proton over here, okay, and then don't know what am I crossing. I think there's I have no idea what am I crossing here. Okay, there you go. Okay, let's talk about how a compound like this, okay, that was the pause. I was trying to draw this structure over here. Okay, so let's talk about how a ring structure would open up upon oxidative cleavage, okay, or hot oxidation. When we break the chains of the double bond, what kind of compound will we be getting or looking at? So imagine here, right, the double bond being cut off, okay? Okay, so look at this like some kind of ring structure, okay? Look at this as some kind of ring structure, okay? At these points, right, where the double bond is, okay, we cut them at these portions here, right? Here, you cut, it opens up. Here, you cut, it opens up. Then you imagine this ring being opened up. Then you get a kind of like a long shaped structure, right? So this is one way of looking at it, okay? If you cannot visualize this yellow tube being cut and open up, right, you can actually number the carbons to figure out what happens at each point. Okay, so by numbering them from I start with the methyl, so the methyl is carbon 1, then I name them all the way to 10. Okay, then you will see at carbon number 4. Okay, carbon number 4 is where we have the double bond. So let's draw our 10 carbon. 1, 2, 3, 4. Okay, so at number 4 is the double bond, right? So we have 5, 6, 7, 8. Okay, at 8 and then 9, there's a double bond. And at carbon number 10, there is also another double bond. Okay, so what we do is that at all the carbon numbers where we identified the double bond, right, we will draw the double bond O at this point. See at number 1, double bond O. And since there is no hydrogen there and CH3 is a ketone, so I will draw number 1 as a ketone. Okay, then CH2, CH3, okay, so this will continue on. And then at number 4 is another ketone, so double bond O. Okay, we cut at this point, right? So let's make this a ketone. Now, okay. Then number 5, 6, 7, 8, nothing happens. We just do a CH2 all the way. Okay, so CH2, CH2, another CH2 at 7, another CH2 at 8, another CH2 at, nope, not at 9 is a double bond O, okay, where we have a ketone. Okay, at number 10, this carbon over here has a hydrogen, so it turns into a carboxylic acid. And since it's alkaline oxidation, hot alkaline oxidation, the hydrogen loses the acid, so it will be a COO minus. All right. Okay, so either you look at it as you can look at it through the yellow chain, or you look at it through the numbering way, whichever suits your understanding or remembering, or rather indicating what happens at each point better. Yeah. Okay, so now back to co-alkaline oxidation, or mild oxidation. Okay, this thing also called mild oxidation, right? So across the double bond, you just need to add OH each, okay, and then remove the double bond. Okay, so they each take on the carbon, sorry, they each take on the OH, and you remove the double bond. Okay, now I share my whole screen again, just to have a better view. Okay, just check your answer for your co-alkaline oxidation. Okay, now this is cold oxidation, but it's acidic. Okay, it doesn't really impact at this point because there are no alkaline groups here that would react with acid. Okay, so yeah, you kind of like just do the mild oxidation. Okay, even though it's acidic, we don't have any alkaline groups here, so it will not react with the acid. Now again, hot alkaline KMnO4. Okay, if they actually tell you what kind of alkaline, like NaOH, right, then you have to indicate the actual spectator ion that binds with the carboxylate salt. Okay, so if you look at this COOH, right, okay, we're gonna put this negative charge and then add a Na plus, okay, because our alkali is sodium hydroxide, right, so you better put a sodium with the carboxylate salt. Okay, now over here there's a mistake over here, because this is a CH3. So remember, all your methyl benzene undergo oxidation, right? And then they give you a carboxylic acid, okay, or benzoic acid rather. Okay, so this will be COOH. Here, the OH is not wrong in the sense because no oxidation occur, but the teacher circled the OH because, okay, let me commentarize the correct part. Okay, the CH3 group has to be changed to a COOH upon oxidation. Okay, so any carbon attached to the benzene ring that is not tertiary will oxidize. If let's say you have something that is a tertiary carbon here, like if you have three CH3 groups attached to this carbon, then it will not undergo oxidation. All right, it will remain unoxidized. Okay, phenol or the OH group, again, will not undergo oxidation. Okay, this part over here will not undergo oxidation. Okay, so what happens is actually phenol will react with alkali. Okay, so again, you will get what we call sodium phenoxide. Okay, so the OH would actually give off the H as an acid to sodium hydroxide through a neutralization or acid-base reaction. Okay, now you look at this carbon over here. Let me circle it. Okay, this carbon over here, it's a tertiary carbon like I mentioned. So this carbon actually doesn't undergo any oxidation. Okay, so it stays as it is. But if you notice that we have a double bond, so this double bond will break. Okay, it will break, and then we will get our we will get a carboxylic acid on this side. Let me get to the right page. I must have slipped the page. Okay, there are some handy notes here. If this carbon is tertiary, it cannot form COH with, well, it just can't form COH, okay? So it will just stay the way it is, okay? Okay, there's a bit of mistake here. Okay, the compound that is formed after being cleaved is not carbon dioxide and water. It's actually a ketone. So what we will get is a propanone. Okay, we haven't learned this chapter. It's under aldehyde and ketones. But I mean, you haven't learned the name is propanone, or maybe you have learned, but you're probably not very familiar with naming it. Okay, but be familiar with writing the structure as CH3COCH3. Okay, because of two R groups present, you will be getting a ketone that does not further oxidize to a carboxylic acid or carbon dioxide or water. Okay, so you'll get a CH3COCH3. Okay, are we at the next compound? Is it time for the next compound? Okay, now, this one over here, right? It's a primary alcohol, so it should have given carboxylic acid. Okay, primary alcohol oxidizes to a carboxylic acid. Okay, so let's just put the COH there so that it's a benzoic acid. So I've got some notes to write. Okay, now this carbon over here is not tertiary. Okay, it has a hydrogen with it. So actually this entire thing should have been oxidized to give you a carboxylic acid. Okay, remember it's not tertiary, so it can oxidize. If it is tertiary, it cannot form carboxylic acid. Okay, then same story, that part that was broken off should have also given you propanone. Okay, so that's the missing one. I'll probably cover it in a bit. Okay, remember this carbon over here, yeah, I repeat again and again, this carbon over here is not tertiary. Okay, if it's primary or if it's secondary, it can oxidize. Okay, the entire chain just breaks off and gives you carboxylic acid. Right, then there's a double bond here that has to undergo cleavage. Okay, that's a line. Okay, there's a double bond here that undergoes cleavage. So, sorry, let me mute this. Okay, so actually this part over here, right, after oxidizing, should give a like a, what do you call this? Let me see. Um, carbon dioxide and water. Okay, so yeah, this part gives off carbon dioxide and water. Then on the other side of the double bond, we will also get a propanone and just propanone. Sorry, let me go back to full screen. Okay, yeah, this section over here, okay, is a propanone. Let's change this to blue to indicate the section it represents. Okay, then just think of the, yeah, just color categorize the different sections that would have been oxidized. All right, so just check your answers. So yeah, then last thing to take note that if you are using NaOH again, okay, take an extra step to make sure that any acidic group will undergo an acid-base reaction. Okay, so let's change this to CO minus Na plus, making it a sodium carboxylate salt. And similarly, this carboxylic acid group here will also turn into a sodium carboxylate salt. Okay, then now just check your product, okay, for the different electrophilic addition. Okay, just need to add the of halogen, and then for this part, just do the necessary hot oxidation. You get there's a terminal carbon there, so you get carbon dioxide, and then the non-terminal carbon becomes a ketone. Okay, and 1 Br for each. Oh, sorry, this is for drawing the reactant. Okay, so since here there are 4 bromine, there should have been 2 double bonds in the original compound. Okay, so for every pair of bromine adjacent to each other, we will draw a double bond. Okay, sorry, so for the previous part, it's the same story. Okay, well, this is the mild oxidation, right? So again, adjacent OH, we will add a double bond. Okay, so this one, again, for this product to happen, we will have a alkene at where the double bond O is. Okay, and this one, because there's double bond O at these 2 locations, right? So it's very likely that they were joined to each other previously because these 2 are ketones. Okay, so this oxygen and this oxygen over here, okay, they are from the same carbon double bond that was broken up. So a cyclic organic compound was being broken up to form this compound. Okay. And then since this point has a CH3, so that's why the square has a little line jutting out, all right, representing the alkyl, the methyl group. Okay, then over here where we have a OH, this is actually addition of water. So double bond would be where that OH point is. Okay. Okay, so addition, I think we didn't really do this part on arene, so I'll just skip through this because this exercise was not given to you all. Okay, so okay, that's all for the homework we went through. So let's close this. Okay, now we move on to halogen derivatives. Okay, I believe I went through the reagent and conditions. So let's go back to the reagent and conditions and okay, what am I doing? Okay, I'm pointing at something. No idea what else I'm doing. Okay, no, I'm doing a recap, okay, on the reactions of halogenous alkanes and ways that we can produce halogenous alkanes. So I'm just going back to revise something that we haven't been touching for about 2 weeks because we were dealing with ionic equilibrium. Okay, so let's go back to this. Oh yeah, don't forget to do your ionic equilibrium homework. I didn't go through today because apparently many of y'all didn't do it lah. So try. Okay. So first question to y'all is, how are halogenous alkanes? Oh wait, I think. Okay, so I should go back to equilibrium. Okay, I think I was looking at the homework. I think so nobody attempted it. I think I mentioned I suggest that you all attempt from question 28 onwards. Okay, so just try the questions from question 28 onwards, at least. Okay, I think because everybody was complaining about too much homework and a lot of things to do in school and a lot of extra school activity outside, tuition outside, dance outside, sing outside, don't know, school practice, CCA, whatever. So you have no time to do the homework. So you ask for a card, right? So I actually asked maybe you all can do a teamwork okay, each person take on one question, then we will go through next lesson. So I think you all will arrange among yourselves how to arrange this. Now I also have some ionic equilibrium notes for y'all. Okay, so each of y'all take one copy. Okay, so this is just a recap on the ionic equilibrium calculations. Okay, now so basic calculations like concentration of acid and base. Okay, if it's a weak acid or weak base, we will use the formula square root Ka times C or square root Kb times C. Okay, then if you want a pH or pOH, that's standard. Just do a negative log on the concentration of H plus or OH. Now for buffer, okay, they have a similar equation. Buffer equation is pH equals to pKa plus log concentration of salt over acid. Okay, so if your concentration of acid is equals to the concentration of strong base, right, uh, then the concentration of salt will be equal to the volume of the base you added. Similarly, if your concentration of base is equals to the concentration of strong acid, then the concentration of salt is the volume of acid added. Okay, then the amount of acid you have will be the volume of acid you started with minus the volume of base you added. So in a way, you actually just have to deal with the volume. Okay, now, but if the concentration of the acid and the base is not the same, all right, then we will have to deal with number of moles by dividing the volume. All right, so it's easier, of course, if you have the concentration of them being the same lah. All right. Now remember MBC, maximum buffer capacity. Okay, pH equals pKa, pOH equals pKb. Okay, then we have the salt hydrolysis equation. Now if you have the strong acid or base in the new volume, then we will use this formula. Okay, the number of moles of excess base. Okay, please do this correction on your notes. Okay, make it number of moles. So number of moles of excess acid or base over the new total volume, okay, which is adding acid and base together. Okay, now flip on to the next page. Okay, it's actually an indication of how the volume works with polybasic acids or polyacidic bases. Okay, so like for example, if I have like H3A, okay, so an acid that has that's tribasic. Okay, so assuming same volume, okay, so I will, for whatever X volume of H3A I need, right, I have, right, okay, upon adding half the amount of acid, I actually produce a buffer, right? So X over 2 of NaOH used will use up X over 2 of the H3A and produce X over 2 of the H2A. Okay, remember I told you all the acid has to be removed 1 mole by 1 mole of H plus. Okay, so the this X over 2 added to H3A will be converted to the H2A minus. Okay, so then if I add X moles of or rather X volume of NaOH, then all my H3A will be converted to H2A minus. Okay, now I continue adding. Now I add 3 over 2x, okay, of the NaOH, then my H2A will now convert to HA2 minus. Okay, so half of them get converted, half of them stays as H2A minus. Okay, then if I add where am I now? If I add 2x, okay, then all my H3A will form HA2 minus. Okay, that means it loses 2 moles of acid. Okay, 2 moles of acid. So I'm left with 1 mole of acid. So now I add another x over 2 of NaOH, it will convert again. Okay, so far so forth. Okay, so just be clear on the conversion of polybasic acids. Alright. Alright, now am I done with ionic equilibrium? No, I'm not. Okay, here is a what do you call this? A practice sheet or maps drill, okay, for your organic chem. So yeah, just practice on this and then yeah, you can throw it away after you are done. Okay, don't keep these things. These are like rough paper for you to test your memory. Okay, so each of you all just pick 1 or 2. Okay, and somebody keep for Naomi. There's also some MCQ practice to be given out to you all. So I will give you all the not hydrocarbons. I'll give you the chemical periodicity MCQ. Okay, so each of you all take 1 copy. I'll give you all hydrocarbons also. We'll probably go through hydrocarbons MCQ next week with the chemical periodicity. Okay, so take the MCQ, go back and practice. But most important, don't forget to practice your ionic equilibrium. Okay, the solution also provided already. No excuse to not try, right? Okay. Okay, let me fast forward the homework distribution. Still at homework distribution. Okay, done. Okay, let's move on to halogen derivatives. Okay, so back to the topic I was saying. Okay, let's do a recap on halogen derivatives. Okay, so now let's can you tell me what are the ways I can form halogen derivatives? Okay, so the first way forming halogen derivatives. Okay, alkanes undergo free radical substitution. Okay, FRS for short, but free radical substitution will give me RX, okay, my halogen derivatives. Okay, conditions are Cl2 UV lights. The second way is alkene undergo electrophilic addition of either you can look at it as adding hydrogen halides at room temperature or halogens in CCl4, no UV light. Okay, then you get your halogen derivatives. Okay, so actually there's a third way. I think I will cover it in alcohols. Okay, but alcohols can undergo nucleophilic substitution to form halogen derivatives. Okay, so we will cover this under alcohols a bit later. Hopefully next lesson. Yeah, maybe next lesson. Okay, so now let's talk about what reaction halogen derivatives can undergo. Okay, first one, most important in the chapter is nucleophilic substitution. Okay, we also say this reaction is hydrolysis. Okay, where RX or halogen derivatives react with strong alkalis such as potassium hydroxide and sodium hydroxide under reflux. Okay, and then it will give you alcohol. Okay, other reaction it undergoes is elimination. Okay, by reacting with KOH in ethanol under reflux. Okay, they can form alkenes. Okay, they form alkenes. All right. Then after forming alkenes, what other reactions can halogen derivatives undergo? Okay, yes, potassium cyanide, okay, KCN in ethanol reflux. Okay, this will form nitriles, okay, the RCN group. Okay, another reaction is primary amines can be formed, again via nuclear sub, okay, using ammonia in ethanol. Concentrated ammonia in ethanol, heated in a silt tube. Okay, remember the very, very odd condition that requires to be heated in a silt tube. Okay, I believe that's all the reactions I know that we undergo for halogen derivatives. I don't think they undergo oxidation. No, they don't. I've written it very neatly in an upside down manner, but I believe it's legible. Okay, so these are all the reactions that undergo. So now let's talk about the mechanism. Okay, so what's the name of this mechanism? Okay, it's nucleophilic substitution. Now, what am I doing here? Okay, so this is the general reaction for nucleophilic substitution. Okay, RX with any strong alkali, okay, will give you a alcohol. Then the spectator ion will combine with the halide to give you a potassium halide. All right. So talk about nucleophilic substitution. Now there are two kinds of nucleophilic substitution. The first one is SN1. Second one is SN2. Okay. What do the 1 and 2 in nucleophilic substitution represent? Okay. Take a guess. Okay, this is where everybody kind of like throwing funny guesses to me. Okay, think about it for a while. Okay, but secondary and tertiary halogenal alkanes can undergo SN1, whereas primary and secondary halogenal alkanes undergo SN2. Okay, so what do the 1 and 2 represent? Obviously not the kind of halogenal alkanes that undergo nucleophilic substitution, right? Okay, so actually, you see, this is 3 and this is 2, so right, 1. Okay, so tertiary undergo SN1, primary undergo SN2, and secondary undergo both. Well, it's kind of like a mixture, certain percentage of SN1 and a certain percentage of SN2. Okay, how it works is depending on how the structure of the secondary, right? they will have different percentages of SN1 and SN2 going on. Okay, but tertiary dominantly is SN1 and primary dominantly is SN2. Okay, so let's look at the tertiary undergoing SN1. Okay, so we have a tertiary with a slow step. Okay, it will give you a carbocation. Okay, and halide. Okay, so halogenal alkane, as you can see, a tertiary, right, will undergo nucleophilic start via SN1. So steps you need to note is which atom carries a negative dipole and which carries a positive dipole. And then the direction of the curly arrow will be from the bond to the atom carrying the negative dipole. Okay, so take note of terminology like electron deficient carbon. Okay, so this carbon here is electron deficient. Okay, so this goes to the Cl via heterolytic fission and it forms a carbocation intermediate and a chloride. Okay, then the carbocation intermediate will be attacked by the nucleophile. Okay, I think the minus should have been on the H side, but it's okay. Okay, so the lone pair on the OH representing it as a nucleophile will attack the carbocation, and through the fast step, you will form your alcohol, alright? And then the halide basically just floats around as a spectator ion now. Well, it's not a spectator ion because in the previous part it was attached to the halogenal alkane. Okay, but this is how you form the product. Okay, this chloride will probably be floating around the solution with the potassium ion. Now let's talk about SN2, okay, where this is for secondary or primary halogenal alkanes. So I'm going to draw this in a three-dimensional manner with the radial and solid wedge. Okay, let's draw the most easy halogenal alkane, primary halogenal alkane. Then via the slow step, I change the position of my Cl. So correction, take away my mass. And then I get OH minus. Okay, so this Cl carrying a delta minus, then this electron deficient carbon will carry a delta plus. Okay, because this carbon here is electron deficient since it's attached to a electronegative chlorine, which pulls the electron to itself. Okay, then this one is CH3, then this is C. I don't know why am I circling about. I'm probably talking about steric hindrance maybe. I'm trying to figure out what am I saying at this point. I can't, so I'm just gonna mention. Okay, so the reason why carbocation but the reason why tertiary halogenal alkanes undergo SN1, right, is because they have too many alkyl groups which cause steric hindrance. Okay, so it makes it difficult for the nucleophile to attack. Okay, whereas if you look at this on this side where the SN2 is occurring, there is less steric hindrance, so this nucleophile can actually attack the electron deficient carbon in the primary halogenal alkane. Okay, so again, take note of the arrow direction, okay, from the negative to the positive, lone pair to the carbon, electron deficient carbon. Okay, now then you will have the slow step. Okay, you will have the slow step, and then here's the carbon. I have no idea who's asking me what at this point. Okay, I really have no idea. This is why you shouldn't miss lessons, because you'll be caught up in accidents like that when my recording did not catch the audio. Sounds like a very engaging conversation, but I really cannot remember what was going on. Okay, we're talking about backside attack. Okay, so the OH does like a what we call a backside attack, where the OH is temporarily forming a bond on the other side of chlorine, or rather the back of chlorine. And then the chlorine will slowly leave from the front. So OH joins from the back and chlorine leaves from the front. Okay, then this is what we call the transition state. Okay, and the OH carries its charge into this ion. So this is what we call the transition state. Okay, so you have to put a square bracket with a minus, representing the minus that came from the OH. Okay, so it's my attempt to write transition state upside down. As neat as I can. Then via the fast step will be the chlorine totally leaving the group with the charge and leaving behind the alcohol that was formed. Probably talking about how the charge is carried. Okay, so yes, the charge is carried by the chlorine out of this molecule. And that's via the fast step. Okay, so via the fast step, the OH joins in via the backside attack, and the chlorine leaves, okay, as a Cl minus. We should have written a plus Cl minus here, but looks like I did not. Instead, I zoomed out for better comparison view of the two. And my phone was not cooperating. Okay, so just take note that this reaction, right, is SN1 because in the slow step, it only involves one molecule. Okay? Whereas on the other one, okay, it involves two molecules in the slow step. Okay, so it's SN2. Okay, so the pause just now was actually, I just recall, I was asking everybody to guess why is it SN1 and 2. And Tiagesh mentioned unimolecular and bimolecular. Okay, so in the first one, right, okay, because only one molecule or unimolecular is SN1. The second one, since there's two molecules, is SN2 and bimolecular. Okay, then also take note that in SN1, there's two steps. It's a two-step reaction, whereas in SN2, it's a one-step reaction. Okay, I repeat, SN1 is a two-step reaction, and SN2 is a one-step reaction. Yes, it's inverse, so it's not the reason why it's been called 1 and 2. Okay, 1 and 2 is actually referring to the order of reaction. Okay. Oh yeah, do take note that for RI, you don't need to draw the transition state, but I still strongly recommend because I think most school I've seen actually have to draw the transition state. Okay. So this is the rate equation for the SN1. Okay, is rate equals to K Rx, since that is the molecule in the slow step. And SN2 is Kr2. Wow. Is rate equals to K times the Rx times the OH. Okay, so since there's two molecules involved, then it's SN2. Okay, now here. This compound here is a tertiary, or rather it's just a carbocation, whereas this intermediate here, let me shift it up. Okay, it's in a transition state. So they both have different type of intermediate. Okay, for SN1, carbocation intermediate, SN2, transition state intermediate. Okay, so that's where the difference is. And also take note of the number of groups. Okay, for the carbocation, there are 3 groups attached to the carbon, whereas the transition state has 5 groups attached to the central atom, or the central atom carbon. Alright. Okay, so I believe I'm probably explaining why secondary and tertiary undergo SN2. Let me see, why am I going through? Inversion of configuration. Okay, okay. So I was explaining in the SN1, okay, we have a difference in the kind of compound form. Okay, SN1 gives you a racemic mixture, whereas SN2 gives you inversion of configuration. Okay. So the racemic mixture comes from the carbocation intermediate. I don't know whether this is the right time to explain. Maybe I've already done so. Okay, let's see if I go back there. I will go back to this explanation. Okay, because since I'm here, I'm going to just talk about the inversion of configuration. Because of the backside attack, right, the Cl that was on the left side of the molecule has now turned to a OH on the right side of the molecule. So this is called inversion of configuration, right? Okay, there you go. Racemic mixture. Okay, how does this racemic mixture come about? Okay, if you look at the this molecule over here, right, it's trigonoplanar. Okay, this carbocation intermediate is trigonoplanar. So this is me trying to draw the trigonoplanar carbocation intermediate. Okay, and what happens is that okay, because this compound I drew does not have optical isomerism, so I just drew another possible compound that could have optical isomerism to illustrate. Okay, so anyway, imagine this nucleophile. It has a 50% chance to attack on the top and a 50% chance to attack on the bottom. Right, so this 50-50 gives rise to a 50% of each type of optical isomerism. And remember, if you have 50% of each type, right, they cancel out in optical activity. Okay, so the cancellation in optical activity, of course, results in no optical activity, and this is called a racemic mixture. Okay. Okay, so I guess my hand shaking represents no racemic mixture. Okay, yeah, this is the light. Okay, then it's rotated because of the optical isomer. Then the other 50% rotates it back to the straight line, so resulting in no optical activity. Okay, so this is the nucleophilic substitution lesson, I suppose. So back to the my notes. Okay, you would notice the whatever I just mentioned is actually in the right side of the table, giving you an explanation on the differences on the mechanism and how they differ. Okay, so do take note of the difference. Okay, like firstly the primary versus tertiary or secondary that will undergo the reaction for SN2 versus SN1. The SN2 represents a second order reaction, SN1 represents a first order reaction, and of course they are named after the rate equation. Okay, so if you look at rate, then for SN2 is rate equals to K times nucleophile times the Rx. Whereas for SN1 is just rate equals to K times the Rx. Okay, then the one step, two step reaction, the carbocation, the transition state, the 5 group, the 3 group, the process, and the kind of product they will form if it's optically active halogen alkene. Okay, so this is a very summarized comparison of SN1 versus SN2. It's good to be very familiar with this. It really it tests your understanding on this. Okay, so the next part in this chapter that's very important is hydrolysis or the comparison on hydrolysis. Okay, the ones you really need to know is in this table over here. Okay, iodide being the largest and the longest bond will be the easiest to hydrolyze, followed by bromide and chlorine. Okay, so just take note that iodo alkanes is the easiest to hydrolyze or break the CX or CI carbon and iodine bond versus the carbon and chlorine bond. Okay, then tertiary is the most easy, whereas primary is the most difficult. Okay, this is due to the stability of the carbocation they form. Okay, because tertiary Rx forms the most stable carbocation, so that's why it's the most easy to break or hydrolyze. Okay, then okay, next part is here the difference between SN2 and SN1. Okay, why do tertiary undergo SN1 and why do primary undergo SN2? Okay, the reason is because the tertiary halogen alkane have a steric hindrance, okay, due to having 3 electron donating R groups, and the carbocation that is being formed is more stable relatively. Okay. Now the next thing you need to know is this is super important, super important. Okay, I know I'm a bit losing energy after talking for 2 hours on my own on this recording, but this is super important. Okay, chlorobenzene, the chlorobenzene cannot be hydrolyzed. Okay, so take note of these two. Okay, I don't know what am I doing right now. The nucleophile attack this carbon. I don't know, am I pointing at hydrogen? Okay, enlarge. Look at the enlarge drawing. And I'm writing something. Steric hindrance. Okay, so I was explaining. Okay, sorry. So call back to my explanation. Okay, so because tertiary halogenoalkanes undergo steric hindrance, they cannot undergo not undergo steric. They have steric hindrance, so they cannot undergo SN2. Okay, there's too much clutter or obstruction for it to for the nucleophile to attack a tertiary halogenoalkane. So they actually undergo heterolytic fission on their own to form the stable carbocation, okay, due to having 3 electron donating groups to make it a stable carbocation. Okay, then on the other hand, since primary carbocation is not as stable, then they cannot undergo SN1 or hydrolyze on its own through heterolytic fission. You know what am I writing? Pointing at here. This one, okay, I'll probably explain that it undergoes SN2 because it cannot undergo SN1 due to lack of stability, the carbocation being formed SN1. So 20 minutes, very long. Okay. I think many times I repeat myself. I just realized how often I repeat myself in one lesson. Because in the recording, I tend not to repeat myself since I hear myself more. So again, primary halogenoalkanes undergo SN2, tertiary undergo SN1. Okay, one due to the stability of the carbocation form, and the other due to the uh, lack of steric hindrance. Okay. So now I'm done talking about SN2, SN1. Let's talk about the hydrolysis. I'm still talking about hydrolysis of tertiary versus primary. Okay, here. Okay, this is me explaining why the CCl bond in chlorobenzene is impossible to break. Okay, because the p orbitals, okay, of the chlorine, okay, overlaps with the pi orbitals of the benzene ring. Okay, I think the pause just now was me getting everybody to attempt the answering. Okay, so anyway, due to this overlapping, then the CCl bond is strengthened and is too strong to be broken. Hence, chlorobenzene cannot hydrolyze, or the CCl bond in chlorobenzene cannot be broken. All right. So again, because the CCl bond is strengthened by the delocalization of the lone pair of chlorine, okay, into the benzene ring, you can also say the p orbitals of chlorine with the pi orbitals of the benzene ring. All right, then the aryl Cl bond or the benzene with the chlorine bond is too strong to be broken. Okay. Attack of nucleophile is also made difficult by the steric hindrance caused by the benzene ring, and the pi electron clouds will also repair the lone pairs of the incoming nucleophile. Okay, so okay, here is me explaining that if you this CCl bond is impossible to break, but if you have a CCl bond in an alkyl group attached to a benzene ring, this is possible. Okay. So the left impossible, the right possible. Okay. Now moving on. If you have multiple chlorine, also cannot. Okay. Another one is when you have a chlorine overlapping with the pi orbitals of an adjacent double bond, CC double bond. Okay, the halogen attached to a adjacent alkene, right, will have an overlap of the pi orbital with the p orbitals of the halogen. Again, this overlapping gives you a stronger bond, making it difficult or impossible to hydrolyze. Okay, so the pi electrons of the alkene group will overlap with the p orbital of the halogen, hence making it not possible to hydrolyze. And yeah, that's what it is. Don't know what else am I pointing at, spending such a long time explaining. Yeah. I remember. I was actually making a recap on this chapter we did previously last year on hybridization and resonance, right? So just think of the overlapping arising due to resonance, hence they cannot hydrolyze. Okay, so you can see here, okay, this is not reactive, it cannot undergo hydrolysis. Okay, so remember the keywords, okay? The overlapping of p orbitals of chlorine with the pi orbitals of benzene ring, and overlapping of p orbitals of bromine or halide, any other halide overlapping with the pi orbitals of the alkene group. Okay, so this form of overlapping is done through resonance. Okay, so this overlapping due to resonance basically makes it difficult for it to hydrolyze. Okay. All right. I should be almost done. Another 11 minutes. Not sure what else am I talking about for the next 11 minutes. Drawing a long chain. Okay. Okay. I'm talking about Sayzeff's rule. Okay, when it comes to elimination. Okay, so question is, we have two possible products from the elimination. Okay, remember the condition, KOH in ethanol reflux. Okay, so I either have this product over here. Okay, so now question. I drew these two products A and B. Which one do you think would be the major product? Okay, or rather, I think I asked whether A is going to be a major or minor. So Diagesh says that it's going to be major. Shrutika says major. Uya also say major. Don't know whether it follow the crowd. Okay, but you guys are correct. Okay, this is the major because by Sayzeff's rule, okay, the opposite of Markovnikov's rule, the poor gets poorer. Okay, don't write that. Don't write that in your answer. Okay, poor gets poorer cannot be written in your answer. It's just a way to help you all remember. Okay, but by application of Sayzeff's rule, okay, the hydrogen is removed from the carbon that has less hydrogen. All right. So if you look at the compound above, right? Okay, there there is one carbon that has less hydrogen. That is where the hydrogen will be removed from. So that will be the major product. Then the other one where the hydrogen is removed from the carbon that has more hydrogen, that will be the minor product. Okay, so I repeat, Sayzeff's rule, okay, hydrogen is removed from the carbon that holds less hydrogen directly, of course. Okay, you see this one, I draw an arrow. There's only one hydrogen. Or two. The other one has three. Okay, so it will remove from the carbon that has two hydrogen. Alright. Okay, so just take some time, digest Sayzeff's rule. You don't need to explain why that is the major product, but you just need to be able to identify that it's the major product. And if the question asks you for only one product from the elimination, right, you should always draw the major, not the minor. Okay. Then recap on the multiple nuclear sub. I think I was asking, but then everybody was like, can't remember, some remember. Okay, but remember there's this thing called multiple nuclear sub, okay, where after substituting the halogen with ammonia, okay, you form a primary amine. Okay, primary amine will become a stronger nucleophile than the previous one due to the electron donating groups on nitrogen. Okay, so it will attack the halogen, the halogenate alkane, okay, the bromoethane more strongly to get a secondary amine. Then the secondary amine will attack again because again more electron donating group, stronger nucleophile. So it will attack again to give you a tertiary amine. Okay, so this repeats until you get a quaternary ammonium salt. So question here is how do you limit this from happening? If let's say I only want a primary amine, I just want ethylamine, I don't want the secondary amine, I don't want the tertiary amine. So how do I get my product? Okay, so let's think about this. Okay, so this is my primary amine. Okay, so it will subsequently attack and then give you the following products. Okay, so you get a secondary amine. Then you get a quaternary. I think I just finish everything in one line. Okay. But think about it, if I want to reduce the multiple nuclear sub, right? Basically, I just need to reduce the chance of occurrence. So by having less ammonia, okay? Not sorry, by having excess ammonia, okay? Then the chances of it meeting the halogenate alkane is not so high. Okay, so by using excess ammonia, then all your Rx has been consumed and converted, so you won't have further substitution occurring. So to maximize your yield on your primary amine, you should use excess ammonia, or you can think of it the other way and say use limited bromoalkane or halogenate alkane. Okay, and then just flip through anything else I need to cover. I think I've covered everything. The hydrolysis, okay, all the mechanism, reagent, reaction. That do take note the speed at which the halide test will give you the PPT. Okay, basically after hydrolysis, right, the halide ions are free roaming the solution. So by adding silver nitrate, okay, the silver from silver nitrate will combine with the halide ion to give you a PPT. Okay, so the speed at which the PPT forms, right, gives you an indication on the speed of the hydrolysis. Okay, so like iodine, because it hydrolyzes the fastest, so your PPT is almost immediate. And then chlorobenzene don't form PPT. Okay, then also memorize the color of the respective PPT. Okay, silver chloride is white, silver bromide is cream, and silver iodide is yellow. Okay, I will not cover the part on the CFC, you just read up on your own. Okay, generally they don't really test this so much. I'm not saying that they don't, but you should be familiar with this CFC topic since we covered so often, right? Because environmental protection okay, CFC will deplete the ozone layer, and then you just need to know where are the source, how to reduce to protect the ozone layer. Okay, then I was just sharing a story on how I went to Perth, and then there was this man I met with skin cancer. It was quite bad. I'm not sure if you've ever seen somebody with skin cancer. Basically, imagine you fell down and then you scraped a portion of your skin on that. I'm demonstrating. You scrape your skin, right? Then you see that exposed portion that's a bit so-called moist or very white. Then somebody with skin cancer basically loses the outer layer of their skin, and imagine that the exposed layer of your skin on 70 to 80% of your body. So yeah, that's skin cancer. And actually because the hole in the ozone layer is actually residing over Perth, so because of that, or rather this thinning over there, right, there's quite a high number of people over there with skin cancer. Just a story to share. Okay, so anyway, just revise your this one, just read through, roughly know it's not worth a lot of marks, at best 1 or 2 marks only. Which I think, if you can just come up with some environmental prevention for it, then I think you should be fine. Okay, so yeah, I think that's it for the lesson. I've been talking for 2 hours and 11 minutes or 8 minutes. Okay, so okay, I think I will just leave this to the end. I don't think I have anything else to add on. Okay, so make sure you do your MCQ and um revision, sorry, the memory sheets for the organic chem that was given to you, and then that's it. Probably next week we'll do alcohols. Hopefully we can finish alcohols in one lesson, and that's it. Okay, thanks for watching. Sorry the very long and draggy lesson. See you again on Friday. Bye. Can I stop recording? Yes, sir. I can stop recording now. Okay, bye.